Let's now, towards the end of this particular chapter or first part of our course, solve one problem. And obviously, this will be very simple one, but you may be having many variations of similar problems in tutorial sessions. The problem says that you, for example, have a space shuttle payload which has a weight of 100 pounds, so in US customary units, resting on the surface of Earth at a latitude of 45 degree north. So there is a mass, corresponding weight is 100 pounds, and that is located on the surface of Earth, right? And its latitude is given already. So which means that you should be able to work out the effect of Earth's rotation because the gamma value is given as 45 degrees, right? In this particular problem, the value of G is also given corresponding to both non-rotating and rotating Earth. So it's like they already applied the international gravity formula and directly give you the value of gravitational acceleration relative to a rotating Earth, and that is in US units, it's 32.1740 feet per second square. In SI units, it's 9.80665 meter per second square. If you don't account for that effect of rotation of Earth, then the value of G will be different. It will be slightly higher than when you account for that rotation, right? So you have a different value of G in both units corresponding to a non-rotating Earth. The first part of the problem says that determine the mass of the module in both sludge and kilogram and its surface level weight in newtons, right? So let me clearly state what is known, what is unknown. So weight is given in pounds, 100 pounds, and I am asked to determine mass in sludge, right? So this is required in sludge. Similarly, the mass is also required in kilograms, right? But once you determine mass in sludge, you can simply use a unit conversion from mass to mass from US customary units to SI. So the mass is also required in kilograms. And the third quantity asked is the surface level weight in newtons. So W value, W is also required in newtons, right? So this is one given information. Weight is 100 pounds. You are asked to determine mass in sludge, mass in kilogram, weight in newtons, right? The third thing can be done directly. Third thing is the most easy one because it is simply a unit conversion. Pound can be converted to Newton because force can be converted to force in both unit system, right? So we should have a direct conversion factor between pounds and newtons from our conversion tables. So let's go back and see how many pounds is how much newtons. So these kind of conversion tables are available in your textbook also, and they will be also part of my notes. So you can see that here, pound force, you need to multiply by 4.4482 in order to convert to Newton, right? So it's like 4.4482 should be multiplied by the pounds in order to convert the value in newtons, right? So let's pick that number 4.4482 and go back to the problem. So the third thing was the easiest one. So let's do that first. That third thing. So now W in Newton will be simply equal to 100 multiplied by 4.4482 newtons. So it will be, I think, 445. Yeah, 445 newtons. So the first thing was simply a unit conversion thing, right? So I just keep that separate. Now let's come back to the main problem, that is mass in sludge and mass in kilograms. That would require us to use the value of gravitational acceleration to convert from mass to weight. actually weight to mass, right? So first, for example, keep the problem in US customary units and determine mass in sludge. We know that weight is equal to m times gravitational acceleration, and therefore m will be W over G, right? W is already given in US units as 100 pounds, so 100 pounds divided by gravitational acceleration. So here you have to take care that since you are solving the problem in US units, you should use the value of G corresponding to US units, and that is in feet per second scale, right? The second thing is to decide whether you need to account for the effect of rotation of Earth or not, right? Whether you should use that value of G or this value of G, right? So what is your idea? In this particular problem, should we consider the effect of rotation of Earth on small g or not? We should consider, because the mass is actually resting on the Earth, right? So it is in contact with Earth. Earth is rotating. So therefore, the gravitational acceleration will reduce. So we should use this first value of g corresponding to a rotating Earth, right? And from this, we should pick the value corresponding to US units. So we should use 32.1740, right? Not this one. So let me use small value of G as 32.1740, and that is feet per second square. Feet per second square. This will give you M equal to, that will be 3.11, and the units will be actually pound second square per feet. And this whole thing is actually one sludge, right? So this will be 3.11 sludge. So that will be the value of M in US units in sludge. Same thing you can do for SI system also. You can carry out the problem in SI system and use the value of G in meter per second square, and then you will be actually converting pounds into Newton also. But there is a more direct way also, that since you already have the mass value in one unit system, why not simply convert it using a constant multiplier? So we can convert sludge into kg also. Mass in one unit can be converted to mass in another unit system, right? So let's go back again to the same conversion table and pick up the conversion factor from sludge to kg. And that will give us directly the value of M in kg, right? So we may not need to do that exercise again in SI system. If we want, we can do, but let's simply convert sludge into kg. And if you go back, you can easily pick that number from the same conversion table. For example, in the mass quantities or mass units. So this is the mass units, and it is actually telling you, the second row is telling you, if you want to convert sludge into kg, you should multiply with this factor, right? So you can multiply that factor to convert sludge into kilogram, and that will simply be giving you the mass in kilogram. So is it clear, like first part is okay? Everyone is clear that why I use the small g corresponding to rotating Earth, right? Because the mass was actually lying on the Earth, it was in contact with Earth's surface, right? Now let's see the second part of the same problem, that now the same object is lifted from the surface at a height of 200 miles, right? So miles, you should now know that again the input or known information is in US customary units, right? So weight of that object was 100 pounds, and it is now lifted up at a height of 200 miles, right? And now it is released from that height, and the question is that you should determine its weight under these conditions in both pounds and newtons, right? So the weight on surface was 100 pounds, but now it is lifted at a height and you are asked to determine the weight now. So if an object is lifted from the surface which means now the gravitational acceleration is reduced, right? We studied the effect of two things, height from the surface and Earth's rotation. So now this is the case of Earth's height from the surface. So the small h is given 200 miles, right? The capital R, which is the radius of Earth, is constant. It will be given to you and it will be part of the same conversion table or constant table, right? So capital R is also known. So we will be actually first calculating the gravitational acceleration at that height, 200 miles, right? So now you already know the relationship, that is G naught times R over R plus H whole square, where capital R is the radius of Earth and H is the altitude of a particular mass. You have already plotted that equation, which means that you know that at 200 miles, the value of GH shouldn't be much different than value at the surface, G naught, right? It shouldn't be significantly different, not like 1/4 or half of the value at G naught. So please keep that physical sense in mind while doing all those calculations. Let's keep the problem first in US customary units, and then we can repeat that in SI units if required. So G sub H is equal to G naught times R over R plus H whole square. Now R is given in either kilometers or miles or feet. Capital R is the radius of Earth. H is given in miles. H is given as 200 miles, right? Now consider one important point here, that although we shouldn't mix different units, whenever we are using US customary units, the length should be in feet, not in miles or any other units, right? But we can think of this whole factor R over R plus H whole square as like a dimensionless constant which is modifying G naught to give you GH, right? Why? Because the dimensions of this constant which I just encircled, you can work that out. Numerator is a distance, right? And denominator is also a distance. R plus H is also a distance, right? So in whatever units these quantities will be, they will simply cancel. Those units will be cancelling out each other, right? If you put capital R in miles and your small h is already in miles, so the unit of this whole fraction is like miles over miles. They will be just cancelling out each other. If you, for example, put capital R in feet and convert 200 miles into feet, right? But then again, it will be like feet over feet, right? Whatever factor you apply on the numerator to convert into a particular unit, you have to apply the same multiplier to the denominator also. So which means that this ratio can be considered as like dimensionless quantity, a modifier which is converting G naught to GH, right? So therefore, if I use, for example, the value of G in US units, which is in feet per second square, and now this payload is lifted above the surface, which means we shouldn't consider the effect of rotation, right? It is not rotating with Earth. It is taken somewhere on the surface and released, right? So therefore, it is not in contact with Earth, and therefore, it will not have that reduction which that effect of rotation will have on the small value of G. So we should use in part B, where the object is lifted at 200 miles, we should use the small value of small g, a value corresponding to non-rotating Earth, right? It's not that we consider that Earth is not rotating. It's like the effect of rotation on that object is not there, right? So we should consider this value, the second value, which is the absolute value relative to a non-rotating Earth, this particular value for the second part, right? So I will be using 32.234 now for the second part. So let's use 32.234 feet per second square. multiplied by this factor, right? Now, ideally, I should, in order to remain consistent, I should use the value of capital R in feet, right? Similarly, I should also convert this 200 miles into feet. But again, I know that it doesn't matter. If I keep the units of numerator and denominator consistent, they will simply be cancelling out, right? So why not I put capital R in miles, right? And keep that 200 miles in miles. So for example, capital R, you will know from the same table which I showed that it has a value of 3959 miles, right? And then denominator will be 3959 miles plus 200 miles, right? So miles and miles will be cancelling out each other and you will be getting a factor less than 1, which should be applied to the value of G to get the value of G at a particular height, which is 200 miles here. So when you carry out that multiplication, you will see that the final value of GH will be 29.2 feet per second square, right? So whatever value of your G naught is, you will be having same, whatever units you will have for G naught, you will have the same units for G sub H. And now we determine the reduced value of gravitational acceleration at that height. So therefore, we can now determine the weight that will be mass times the gravitational acceleration, but at a particular height now, not at the surface, right? So since we are working in US customary units, so mass should be in sludge, which we have already calculated. It was, I think, 3.11 here at the bottom. So let's put that in sludge, 3.11 sludge multiplied by 29.2 feet per second square, right? If you write sludge in terms of like pound feet per second square, you will see that the units will cancel out and the final quantity will be in pounds, right? So please carry out that exercise quickly. And this is a point where I said you should be able to quickly work out the unit consistency or dimensional homogeneity. So you know that sludge can be written in terms of pound, feet, and second. If you write that here, you will see that other things will cancel out with this feet and second square, and you will be getting W in pounds, right? And that number will actually be 90.8 pounds, right? So a 100-pound weight on the surface is reduced to 90.8 pounds at a height of 200 miles, right? So this difference from 100 to 90 is because of two reasons. One is that the object is lifted at a height, and secondly, in the first case, we considered the effect of rotation, and in the second case, it shouldn't be considered, and therefore we use the value of G corresponding to a non-rotating Earth, right? So this 10% difference in weight is not only because of the height, it's because of the effect of rotation also. Next question in the same case was that you convert that into newtons, right? Convert this into some newtons. Now you can directly use the unit conversion, right? Because you already have a weight in pounds and you are asked to determine it in newtons, which means it's a problem of unit conversion. So please pick that conversion factor from your table and then apply that, and you will be converting it into newtons. Finally, the last case, that now the same object, which is having height of 200 miles, is now made part of a space shuttle, which start moving, orbiting around the Earth, right? So now it is not constant at a particular height, it is now moving, start orbiting the Earth. And with this new situation, you are asked to determine the weight of that module or object in both pounds and newtons. So actually repeat the same problem, but now consider that that object is not stationary and released from that height. Now it is part of a space shuttle, right? So what difference it will make compared to the last case? Height is same, right? Mass, weight, everything is same. But now that object start moving and start orbiting the Earth. Any ideas? So it is orbiting, which means it is maintaining that 200 miles distance from Earth's surface, like on all sides. So small h is still 200 miles. Small h, which is altitude from the surface, is still 200 miles and it's a constant value, right? So all you need to determine is the weight while it is orbiting, right? So I made it more clear. Determine the weight of the same object which is orbiting at that 200 miles from the surface. So weight, we know already that that is equal to mass times the gravitational acceleration. And since it is always 200 miles from the surface, so it should be having a value corresponding to that height of small g. But that height is constant, right? It is orbiting, so maintaining that altitude all the time. Actually, if there is a person which is actually in that space shuttle, he or she will feel weightlessness. But again, the force with which the Earth is attracting that particular space shuttle or this mass will not be zero. It will still have that weight, but will feel weightless because of a constant free fall situation, right? So mathematically, if you work out the weight of that particular 100 pound, it should be same as if it was stationary somewhere at that particular height. So that movement shouldn't affect its weight, right? And that's what we were discussing actually, that any object in that particular space shuttle will experience weightlessness relative to that space shuttle, right? But the force with which Earth is attracting that object will still be same. So weight of that object will still be capital W is equal to m times gh. And this gh is not a function of velocity of that particular object, right? It is not the function of acceleration of that object. It is only the function of height or altitude, right? gh is equal to g naught multiplied by r over r plus h whole square, right? So the only thing which will modify g sub h is the height or altitude of that object. Its motion won't affect the gravitational acceleration. So the answer would be that there will be no effect on the weight. So the answer would exactly be same as what we work in the part B, right? So same weight, no difference, right? Same weight.